We'll be looking at the occam timer function. Timer is a occam reserve word. It's also sometimes referred to as the clock. We'll be using the try it on emulator, which can be found at this URL, the bottom one. The URLs are in the code, and the code is in the description, so you can copy and paste your way to success. This is basically how the timer function works. We use the reserve word timer to define a clock, which looks like a variable definition, but it's really more like a channel definition. We'll just define a variable delay, and we'll set it to 100. Then we'll say clock gets time read. So time read will get the value of the counter at that moment. Then we'll say wait for equals time read plus our delay, which was 100. And then clock gets after wait for means that it'll look at the value of the clock and not execute that instruction until you get to the time described in wait for. Okay, I thought I'd use a stepper motor as an example of using the clock. That's a little overblown for what we need to do, but stepper motor looks something like this. There's like 4 sets of coils arranged geometrically in a very careful arrangement. Actually, they're more circular than here, but this is just shown for clarity of the driving stages. But each of these coils can be either magnetized or non-magnetized, depending on whether you drive a current through it or not. So the sum of, say, 2 coils being on and a magnet is the magnet will want to notch to the nearest position. And again, these coils are wrapped 360 degrees around the magnet, and they repeat many, many times. And using 2 coils at once gives you a stiffer hold than just using 1 coil at a time. So you can change the position of the magnet depending on which pairs of drivers you drive. This would be the waveform that would just run the stepper motor in continuous angular velocity. So if we look at this real carefully, we can see that here we have the most significant, least significant, and most significant bits set, or a 9. Here we have the 2 least significant bits set, which is a 3. Here we have the 2 middle bits set, which is a 6. And here we have the 2 most significant bits set, which is a C. And then we'll repeat that pattern. So it'll go 9, 3, 6, C, 9, 3, 6, C. C, of course, being hexadecimal for decimal 12. So if we did this, we'd start out at a position. And then when we change the output value, it would go over to the next one, then the next one, then the next one. And then when we come back to the original one, it would go one more. So in essence, it can do 4 steps starting from wherever it started. Now, let's say each of these steps is 1 degree. So you do a total of 4 degrees in one sequence. If you had 90 of these steps, then you would have 360 degrees. So you could step the motor all the way around in a circle, not just 4 degrees, but all 360 degrees by successfully going through that sequence of 4 steps over and over again. You know, I would really use hardware to do this. It only takes 4 flip-flops, exclusive OR, exclusive NOR gates, like Q8 equals up XNOR Q4, Q4 equals up XOR Q8. So very, very simple things, but we're going to do it in software. And the benefit of that is we actually have control of position as well as velocity. And if you actually limited the acceleration rate, you'd have control of acceleration. So you'd have control of position, velocity, and acceleration, which is the basis of a fine motion positioning system. Let's look at our code for the stepper motor using the timer feature. The INMOS Occam 2 reference manual has several sections that talk about the timer, and the Transputer hardware and system design manual also has some really good information about the timer. We're going to have to back up for a second and talk a little about how that works. The timer acts like just like a regular message port. However, it's actually a counter that's just counting up all the time. And the number that it provides you is a 2's complement signed integer, which is a little weird because you have negative time then. But it acts just like any other counter. It counts from 0 up to the highest positive number, rolls over to the lowest negative number, and then counts back up to 0 again. A high priority process uses a clock that takes every microsecond, or a 1 megahertz clock. A low priority process uses a clock that takes every 64 microseconds, or 15.625 kilohertz. Now, the maximum range of that counter is based on the word size for the transputer. So a 16-bit transputer has an int size of 16 bits. A 32-bit transputer has an int size of 32 bits. We're specifically concerned here with 32 bits, which is nice because that gives you a longer delay. Again, once the clock gets to its maximum positive value, it rolls over to its maximum negative value. So a 16-bit transputer high priority process will have a clock that rolls over every 65 milliseconds. So that's quite common. A 16-bit transputer with a low priority process will have the clock that rolls over every 4 seconds. Still pretty common. A 32-bit transputer high priority process will have a clock that rolls over every hour and 10 minutes. Okay, that's getting to be a little more reasonable. And a 32-bit transputer low priority process will have a clock that rolls over every 76 hours, a little over 3 days. So there, it's not going to be a really huge problem. There is a mechanism, I think, internally, which they don't really document that well, where if it'll figure out whether you've passed the time by using the shortest distance method, whether you're closer to the number going positive or negative. So if you only use half of the total possible range, it's going to tend to roll over more correctly. But again, the problem is that when you roll over and you have a negative number subtracting a positive number, it doesn't really give you the result you want. So they have a mechanism to try and cope with that, but it's something that if you really want to have the maximum delay, you might have to come up with some separate mechanisms for rollover yourself. But we're not going to worry about that now because I can't really test it anyway, so I'm not going to guess what it is. So again, starting out at our code, timer is a Occam reserve word, so that's the really important one. And then people by tradition usually call it clock, but you could call it anything you want. I'm going to define a byte called step reg. And this in the real system would actually be memory mapped I/O, which as hardware designers know and love. Byte S, which we'll use for a space character. A Boolean up, so when the stepper motor is going in what we call the up or positive direction, that'll be true, and up will be false when it's going in the negative or down direction. So we're going to use the sign bit of the delay to decide whether we're going up or down, or up is true or false. Then again, we've seen that we need a sequence of numbers to output nibble 4 bits. And so we'll have a 4-byte sequence. A bunch of integers we'll define. Okay, in the memory mapped I/O, I would use place step reg at hex 40 million. That's a little weird number, but if you put in commas, you can see in hexadecimal it'd be thousands, millions, 40 million. People who are used to decimal don't really like hex numbers, but that's what we would call it. And then our port a byte, which goes along with assigning our byte to a memory mapped I/O location, step reg. And then our byte would actually be defined. So Q1 would be bit 0, Q2 would be bit 1, Q4 would be bit 2, just like every normal binary operation. Nothing there. Let's skip over update.delay until we actually use it. We'll come back and look at it later. Count equals 0, max count equals 6 times 4. Remember, we're going to output 4 values for every complete step of the stepper motor, and so we'll go through that 6 times, or 24 total steps. I equals 0. Remember, I is doing 0, 1, 2, 3, 0, 1, 2, 3 if you're going up, or 3, 2, 1, 0, 3, 2, 1, 0 if you're going down. There's our famous space for S. Here's our sequence array of 4 values, and it's going to be 936C. So if you're going up, you'll just repeat 936C, 936C, or if you're going down, you'll repeat C639, C639, C639. The C, of course, in decimal would be a 12. So we'll just start out saying we're in the up direction, or up equals true. Increment I is going to be 1. We're going to have an index for sequence. So it'll be sequence of I. And we'll just start out incrementing by 1. So we'll use +1 if we're in the up direction and -1 if we're in the down direction. So that way we can always just add increment and it'll do the right thing depending on which direction we're going. We'll start the delay out at 100. We'll max count after count, which is exactly the same as count less than max count. But again, YouTube won't let me post a less than greater than sign because they think it's HTML and they don't allow that. So I just have to use this somewhat obscure syntax. Okay, so on to the timer itself. Clock gets time read. So the clock acts just like a channel. That's like a get. And it's going to put the value of the counter right now into time read. And then we want to add the delay to that. So wait for equals time read plus delay. So we want to wait for that number, which is why it's called wait for. Update delay, we'll get to that in a second. And then clock actually waits after wait for. So there's a hardware mechanism that actually causes this process, not every process, just this process, to wait until the number wait for has been counted up to by the counter. And so I have this update delay because we want to be able to change the delay on the fly. That, you know, we can change the angular velocity of the stepper. So let's go ahead and go back and look at update delay. So this is a message from another process. If there's a delay message, we want to wait, but if there's no delay message, we don't want to wait. Now, usually when you have delay gets this, the process would just stop dead until it got a message, but we don't want that. We just want to get a message there and skip if it doesn't. So we use the alt structure. So we're either going to get the delay message or skip, but if we just used an alt, it could do either of these things. So it could just do the skip and just totally ignore the delay. So we want to say priority alt. And this makes sure that not only do we have an alternate, but we always do this one first. So if we do get a message, we would only execute this if there is a message. Then we'd get the delay, which we'll put in delay t temp. Say sign bit equals delay and 80 million hex. Which just gives us the sign bit. And if the sign bit is 0, that's a positive number. This is just like, 2's complement. So we're going to say increment is 1 plus 1. We're going to actually put the delay t into delay. So we'll make the temporary delay the real delay. Say up equals true. And then we'll output the value up just so we can see that something's happening. But if our sign bit is a 1, then we're going to say increment I is -1, up is false because we're going down. Now, how do you change a negative value into a positive value? Well, you subtract it from 0. So if you have -5, 0 minus -5 is +5. So we'll just make it positive. I was actually, again, going to use the exclusive OR function, but that involves the greater than, less than signs, which are forbidden. Then we'll output a string saying down. So we output a string for up or we output a string for down. Then we'll output a string that says new delay. Then we'll output the value of the delay. Then a character return. Again, this skip was because of the alt statement. Now, it seems kind of weird to have 2 no-ops, but this skip corresponds to the message input. But every time you get a message, you have to have a command or you have to do something, and so this skip is the no-op after the message. So that's just the way it normally works. And so we're done with the update delay. We already took the clock wait. Then we're going to output the count that we waited up until. So we'll output wait for, output a space, output the sequence number. So that's the 93612 or the other way around. Then step reg, which again would be our memory mapped IO location, is sequence of I. Then we'll output the string character return. Now we're going I equals I plus increment I. Two things are going on here. Increment can be +1 or -1 depending on whether you're up or down. Plus is the same as the algebraic sign plus, except it won't set the underflow or overflow flags. In some systems, overflow or underflow is considered an exception, and they'll actually stop the whole program for that. So if you want to make sure that you can't cause an error by overflow or underflow, then you can use plus or minus. And then, now that we incremented I, we don't want it to go from 3 to 4 or from 0 to FF. So we'll just keep the two least significant bits. Now the two least significant bits will always increment correctly, but we want to zero out the rest of them. So that's what this little AND statement does. Okay, so we've looked at the stepper process. And now we'll go down and look at the send delay process. Again, the whole point of this is we want to change the delay as we're running the motor. So, the angular velocity could be a certain amount, and then we'll change it because that's what you can do. One of the nice things about doing this, even though we don't have a stop command, it'd be pretty easy to increment it. Therefore, we have direct control of position, velocity, and if you limited the amount you change the velocity, you'd have acceleration control. So if you have control of position, velocity, and acceleration, you have all the elements of a motion control system. How nice. So again, this is completely separate. We're again going to call the timer clock. We'll use a lot of the same language. And we want to do a loop of 4. We're going to update the delay 4 times. We'll wait 400 clock ticks before we update it. Again, this is just saying we're going to go up to 4 times. So we read the clock. We set up our wait delay, which is read clock plus send delay. Then we actually wait here, clock after wait 4. This is just so cool. I can't believe it. This is a hardware guy. This is just a totally wonderful thing. Have somebody can actually put in the comments, a C programmer who does Windows 10, what it takes to actually wait for a value in C or on Windows 10. If you say, I want to wait for 1 second, you probably have to set up interrupts and interrupt handlers and all sorts of nonsense to get that to happen. Here, bang, just a statement. Here's where we send the delay channel, sends the variable delay. Then we're going to subtract 50 from the delay, and we'll increment our count by 1. Now, this seems a little weird that if we started at 90, we start subtracting 50, 90, 40, minus 10, minus 60, minus 110. Well, what are we going to do with minus? Remember, the minus bit is just the up-down direction. So we're always going to use the magnitude of the delay, and then the sign bit will be whether it's up or down. So let's go ahead and run this thing and see what happens. Okay, so this says we have positive numbers here. So we went from 345 to 591, which is a little over 90, but that's partially because we have all these output statements. And then here we got a new delay. Remember, we started out at 100 and we went to 90 when our process said 90. We output a few of them. So we're using the 12.936, 12.936 sequence. Delay went to 40. Now the delay went to minus 10, but that's really down 10. You don't really want to think of it as minus. And then we did 12.639, 12.639. Our next and final fourth delay would go to 60. And again, we're doing the 12.639, 12.639. So here we were doing 3.6, 12.9, and now we're doing 12.639. So we're going in the opposite direction. So that's it for our stepper motor controller.